Calculating KSP from solubility. The strategy for solving this type of problem is similar to that of finding the Ka for a weak acid from the pH of a solution. In those problems, the hydronium ion concentration was found from the pH, and then an ice table was used to find the concentrations of weak acid and conjugate base. When molar solubility is known, the equilibrium concentrations of the ions can be determined from the solubility and the ratios discussed in the previous topic. These values are then placed into the KSP expression, and the value for the KSP is calculated. The ice table is not needed since the ratios of the ions to the compounds are used. Example 1, calculating KSP. The molar solubility of lead 2 bromide, PbBr2, is 1.0 times 10 to the minus 2 moles per liter at 25 degrees Celsius. Calculate the solubility product, KSP, for this compound. So let's start with our dissociation of PbBr2 solid into Pb2 plus ions and 2 Br minus ions. The molar solubility, which is given as 1.0 times 10 to the minus 2 moles per liter, refers to the ion with the lower molar ratio. So right here we have 1 mole of lead 2 plus ions and 2 moles of Br minus ions. So the one with the lower ratio is the lead 2 plus. So we set that equal to the molar solubility, 1 times 10 to the minus 2. And then the Br minus ion will be twice that, since 1 mole of PbBr2 produces 2 bromide ions. So we multiply by 2, or it's also 2 times 10 to the minus 2. Then we can substitute the molar concentrations into the KSP expression, which is just the concentration of the lead 2 plus ion, 1 times 10 to the minus 2, times the concentration of the Br minus ion, 2 times 10 to the minus 2, squared. Remember, we need to include the coefficient in our KSP expression as an exponent. We get a KSP equal to 4.0 times 10 to the minus 6. Example 2, calculating KSP. Given a saturated solution of iron hydroxide with a pH of 11.3, what is the KSP of the solution? And B, if an acid was added and reacted with some of the hydroxide ion, would the KSP increase, decrease, or remain the same? First thing we'll do is write the equilibrium expression and find the concentration of the OH using the POH equation, given that we know the pH, and then we'll find the iron 3 plus concentration using the mole ratio. So here's the dissociation of iron 3 hydroxide solid to iron 3 plus ions and 3 hydroxide ions. And KSP is the iron 3 plus concentration times the hydroxide ion concentration cubed, given this coefficient 3. The equilibrium equation indicates that the iron 3 plus concentration at equilibrium will be 1/3 the hydroxide ion concentration. So the POH we know is 14 minus the pH, or 2.7 based on the pH that we're given. And then the POH is just the minus log of the hydroxide ion concentration, which means the hydroxide ion concentration is 10 to the minus 2.7, which is 2.00 times 10 to the minus 3rd. The iron 3 plus ion concentration, given the stoichiometric ratios, is 1/3 the hydroxide ion concentration, or 6.67 times 10 to the minus 4. And once we know those concentrations, we can substitute them into our KSP expression, 6.67 times 10 to the minus 4 for the iron, 2.00 times 10 to the minus 3 for the hydroxide, and then of course cubed. to give us a KSP of 5.34 times 10 to the minus 12. If an acid was added and reacted with some of the hydroxide ion, would the KSP increase, decrease, or remain the same? The KSP remains the same. When an acid is added, these hydroxide ions are neutralized by the hydrogen ions and the OH decreases. The iron concentration would increase according to Le Chatelier's principle as more solid dissociates, shifting the equilibrium to the right to compensate for the loss of hydroxide ions. As long as the solution remains saturated, the KSP value remains the same.